Alright, so we are back starting again. The tutorial 2, second part. What we are going to talk about now is another way to create a list. And this command is a command that you are going to be using very often, and so it's important to learn how to use it correctly. So what command is it? It's the table command. If you're used to programming in other programming languages, you may have used a for loop to do this type of thing. In Mathematica, a for loop does exist, but you will probably not be using a for loop at all. Alright, so let's talk about table. Table is a way to generate a list based on a rule or a function that you specify. Let me write that down. Table is used to create a list based on a rule. Alright, so let's look at this example here. So in this example, we see that table where we're asking, let's create a list. In my head, when I see the word table, I think, let's create a list. Let's create a list of x squared where x goes from 0 to 5. What will that look like? It will look like 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. The table command, again, we need to keep track of the syntax. And so here's a key thing that the syntax of table has both a function and a list. So that's important. So there are always two inputs to table. There's the function, there's the list. And the output of table is always a list. Like before, it can be a list that has 0 element, it could be the empty list, but the output is always a list. So these two pieces of input to table are the function and the list. The list tells you which values of x will be inserted into the function. And in this second list, this input list, the first element of this list, in this case x, is always the variable that you modify by the function. So up here we had the table was x squared. This x is telling us that that's what's going to be modified in this function. So just like with range, there are a number of different ways that you can specify the set of values of the variable, in this case the set of values of x. So just like in range, you did range of 5, those are the numbers 1 to 5. Here, if we do table of a function where you have x goes to 5, that's saying start at 1, go to 5. So that's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. If the list has length 3, so a variable and then two numbers, this works like range of -1 to 5. So this would be -1 squared, 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. If the list has length 4, then there's going to be increments, right? So if we've got a variable and then 3 numbers after it, you've got the initial value, you've got the ending value, and you've got the increment. 0, 4, so 0 squared, 2 squared, 4 squared, 6 squared, 8 squared, 10 squared. Table also lets you specify the set of values that you want to input into the function. So this is a little bit different than before. This does not have a counterpoint in range, because we're basically doing here is we're specifying the values of x that we want to put into the function. So in this case, we want to say, give me the values of x squared, where x is 0, or x is 10, or x is 2. So we have 0 squared, 10 squared, 2 squared. So the answers are in the order in which the list was applied. So let's do some examples. Let's think about what we would expect in each of these following commands. All right, what do we have here? We have table, so give me a list of negative z, where z starts at 1.5, goes up to 3.5 in increments of 0.5. Okay, so think about what that's going to do. Think about what that's going to do. Pause if necessary. All right, so let's think about the z values that work. The z is going to be 1.5, 2, 2.5, 3, 3.5, and that's the end. So then we want to do negative of z for that. So when we apply this, we're going to get negative 1.5, negative 2, negative 2.5, negative 3, negative 3.5. This period here, so you look at these answers, and this kind of feels a little bit out of place, negative 2 point. This point tells us that this number is not a perfect number. This is a floating value instead of an integer value, for those people who know what that means. Basically, negative 2 is the perfect value, negative 2. Negative 2 point is like saying negative 2.0, it's an imprecise number. I mean, it's precise in that it's negative 2, but when you multiply, you are going to keep a certain number of significant digits instead of being the perfect number 2. Don't worry about that too much. All right, let's look at the next example. Table, all right, SQRT, probably know that means the square root. Table of the square root of b, where b goes from 1, where b, let's actually parse this a little bit more carefully. We have the table, so we want to find the list of things, each of which looks like the square root of something, and then we need to figure out what are those things that we're going to put into the square root. All right, if you look at this carefully, you'll notice that the values that b is going to be this list of objects, right? This is this new type of input that's allowed. This is not b, comma 1, comma 10, comma pi. It's b of the list 1, 10, pi. So that means we're sending each of those values into b, and let's run this. And what we should expect is we're going to take the square root of each of those things. So what do we get? We get square root of 1, square root of 10, square root of pi. That's our list. So what's important is realize that that's going to be different from table square root of b, comma 1, comma 10, comma pi. So this is something maybe you should try in your own notebook. First think about how it's going to be different, and then evaluate it and see what happens. Here's one more example, and it sure feels a lot like the previous example where we had a table of x squared, comma x, comma 5. But already Mathematica is telling us that we should be careful that this is not exactly the same, because if you look at it, the y is blue while the x is teal. And because the x is teal, because this is the first variable, this is what's going to be changing. So we're going to let x go from 1, 2, 3, 4, 5, and the function is y squared. So what's going to happen when we evaluate it? Think, pause the video if necessary. We evaluate it, and what do we get? We get y squared, y squared, y squared, y squared, y squared. Because what was the rule? The rule is whatever x is, the answer should be y squared. All right, so in the comprehension questions, there's a bunch more things to practice. Start to get a feel for how table works, try things out, change numbers, see what you can learn. All right, so now let's try to go to reverse engineer this and think about, let's say we wanted this list of numbers. What table command would work for that? Well, the table command that would work, well, what we need to do is we need to come up with our function, and we need to come up with a variable, whatever variable you want. Maybe I'll call I like I. And then we need to have a range of values for I. So we have to think about what function applies to what set of numbers. And I'm looking at these numbers, and the way table and range work is you need a set of numbers that is increasing at a regular rate. Well, in this case, the feel I get is it's going down and then going back up. And when I think about that, I think that kind of looks like an absolute value function that gets applied to the numbers -2, let me go this way, -2, -1, 0, 1, 2, 3. But when we take the absolute value, then it makes this 2, 1, 0, 1, 2, 3. So we want the I to go from -2 up to 3, and the function is going to be the absolute value function. Now, if you don't know what it is, you just start typing, and you're like, hey, wait, it's probably abs, but let me just check. So if I type in abs, then you click this I button, it opens up in another window, which we can't see because it's this. Actually, let me, instead of doing this, I'm going to hover over abs and I'm going to click the down arrows, and that tells me a quick information about this. Oh, that doesn't show up either. Huh. Interesting, something to learn. When you do this, it says absolute value of z gives the absolute value of the real or complex number z. All right, good. So that's exactly what we want. But absolute abs is a function, so we need to do abs bracket I end bracket, right? And so what we've done is we've now created the function absolute value, we've applied it to I, and when we evaluate it, where I goes from -2 up to 3, so -2, -1, 0, 1, 2, 3, and we take the absolute value of those, we get the 2, 1, 0, 1, 2, 3. So when you're creating, so to determine the correct table function, you need the list of values that the indexing variable takes on. Here it was from -2, -1, 0, ... up to 3, and you need the function that is applied to the indexing variable. All right, so let's look at this now. When I look at this one, oops, that's not how you spell variable, but another thing you should notice here is when we're applying this, what we really want to do is we want to think about what's changing over time. So to determine the indexing variable and the function, think about what is changing in the elements, in the entries of the list. So here, when I look at this, I see 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0, 0, 4. The only thing that's different between them is what that last value is. And so to create this function, what I'm looking at is I'm looking at every single thing looks like 0, 0, something. Let's call it x because we like x. 0, 0, x, where x changes, right? What does x change from? X changes from 0 up to 4. And so this is going to create the way you read this is, I want a list of items that all look like 0, 0, x, where x starts out at 0 and goes up to 4. And that's exactly the structure of what we're aiming for. All right, great. Next, let's talk about, we created some lists. Now, how can we display them? All right, so I'm going to give 2 ways to display them in a way that makes it easier on the eyes to look at. Because look at this list, it's a little hard to read. Imagine if there were 20 of them, it'd be kind of hard to read. The first one is called the table form command. What table form does is it takes a list or a list of lists and puts it into a tabular form. So here is a list of lists. The first one is 1, 2, 3. The second one is 2, 4, 6. The third one is 3, 6, 9. So if we want to display that in a tabular form, we use table form, and now it's in a nice tabular form. A little bit easier to see. Here's another example. Again, here I'm going to define a variable called squares, and it's going to be a table of things that look like I, I plus 1, I squared, sorry, I, I squared. So what we see is we're going to create a list of lists. Each of them looks like I and I squared. So what does that look like? It looks like 1, 1, 2, 4, 3, 9, 4, 16. Those are each I, I squared. And if we apply table form to this, then we're going to get a vertical list where we can really pair up what the I value was and the I squared value is. It's really good for visualizing coordinate data. Another type of way to display information is using the traditional form command. And what traditional form does is it takes the input to the function, and the output is a way you could display it like a person would try to display it. So if we take this same list that we had up here, the 1, 2, 3, 2, 4, 6, 3, 6, 9, and we said, well, what's a normal way you might want to display it? You might think of it as a matrix. So that's nice. Traditional form is also useful when you want to display polynomials. So if we look at this, this is a way to get the Taylor series polynomial approximation for a function. This is, again, I'm bringing in this as an example. You don't need to know what normal is or series is now unless you want to go and investigate that further, which feel free to go do so. When we run this, basically it gives us, if you were to take the Taylor series approximation to this rational function, you get 1 plus x plus 2x squared plus 3x cubed plus ... And if you look at the coefficients, you see 1, 1, 2, 3, 5, 8, 13, 21, and you should be thinking Fibonacci. If you take combinatorics with me, you'll see where that comes from. There's some really cool combinatorial reasons for that. It's related to the power series. And expand this past 10 if you want to learn more. But now this polynomial doesn't look like the way we normally think about polynomials. If you use traditional form, then it turns it around and puts the highest coefficient, the highest degree term first, and the coefficients go in the front. Okay, so those are two ways to take a table and see them in a organized manner. And you might also want to visualize some data. So if we take our coordinates from before, remember how we calculated the coordinates? We wrote down a list of coordinates here that we just wrote down directly. We defined it in the computer, so now we can reuse that variable coordinates. If we do list plot of coordinates, it plots the 3 points, which were 2, 1, 3, 3, 4, 2, on the graph, on a set of axes. There are options to make the axes look exactly the way you want. We're not going to go into those now. This is a way to get a scatter plot of data. You can also connect them using list line plot. So it's creating a line plot from the list of information. Let's do this for another larger set of data. Here's some data. 0, 0, 0, negative 1, negative 1, 1. There's some Fibonacci numbers in here, just to be pretty. And if we take this data and we do list plot of the data, we get all these points. You can check to make sure that each of those points appears here. So the thing that we have here with the list plot, so if we talk about list line plot of the data, it puts them in order. Right, so we started out at 0, 0, and then we went to 0, negative 1, negative 1, 1, 1, 2. This is creating something like a discrete Fibonacci spiral. in this picture. So notice that list line plot comes in order. So the takeaways from these last two sections, this section, is that use table form or traditional form to show the contents of a list in a tabular format, and use list plot or list line plot to show the data visually, show a visualization of the data. All right, so we're almost there. 2 more sections here. Let's say, here's a cool way. Here's a cool application of what we were talking about of a list. Let's say we wanted to simulate rolling a 6-sided die 200 times. If we wanted to do that, we'll use this command called random integer. And what random integer will do is it will give us a random number between 1 and 6 200 times. So if we're rolling this die 200 times, we might want to guess, hey wait, how many times did each number appear? So we can use the tally command, and what tally does is it counts up how many of each of these things appears. So in this list apparently there's 38 5s, there's 27 1s, there's 32 3s, etc. It's a little hard to see, so we can use table form, but maybe we should sort it first. So 1 comes first, 2, 3, 4, and we see that the least number of 1s happened and the most number of 5s happened. If you rerun it again, or change the numbers, or change how many times, you'll get different numbers each time, because rolling dice is a random process. So this is using tally. You can also visualize the data using histogram. This shows us that there were 27 1s, 36 2s, etc. And so it gives you a different visual way to show the data. And we're going to finish off today with 2 very useful commands that we will be using again and again. So these are ones you definitely want to commit to memory. That would be length and total. So length says how many elements are in a list. So if we run this, how many things are in this list? There's 3. There's 3 things in commas in the list. But you have to be careful about what that means. If you run length on this list, length of 1, 2, 3, how many things are there? There's 2, because the first thing is the 1 and the second thing is a list of length 2. So there's a 1 and there's a list, so that's 2 things. Total adds up everything in the list. Total of 1, 2, 3 gives me 6. Nice. So we might say find the sum of the powers of 10 from 1 to 1,000. So to 100,000, excuse me. And so what that looks like is, well, you have a table, and the table gives me 1, 10, 100, 1,000, 10,000, 100,000. So we need a list that gives us the powers of 10. If we add them all up, we get 1, 1, 1, 1, 1, 1. All right, thanks. Now's the time to head over, try out some comprehension questions, and in class we'll be doing some questions related to using these and trying them out and getting more practice. All right, see you later.